get this context problem analysis. So problem A. We have a puzzle. What is the puzzle exactly? Because first we have a candle. We divide it into some number of rectangles. And then we make a puzzle. How we do it? For each tile, squares in the angles of this rectangle should belong to this tile. And then it can also contain some other squares from nearby tiles, but only those that directly adjacent to the side, and that are not directly adjacent to any other side of the tile. And one more restriction is that for any two tiles, for any two adjacent tiles, their border cannot be straight. So what does it give to us to work with? First, we notice that we can, as tiles are not rotated, we can determine which tiles are in the angles, in the corner. Okay. We can also, for each tile that is on the side of the original rectangle, we can determine on which side it was. Because that would be the side with the straight border. Okay, so if n is no more than 3, then each tile is we can uniquely determine each tile because, well, there is exactly one tile on each side. There is 4 corners, and then there is exactly one tile that is not on any side, so it's obviously in the center. So the only interesting case is if n is 4. But well, then we have 2 tiles on the top side, 2 tiles on the bottom side, 2 tiles on the left side, 2 tiles on the right side, and 4 tiles in the middle, which leads to a total of so there is exactly this amount of ways we can interchange these tiles. But this number is not that big. So we can just brute force through all possible permutations of tiles. All the permutations that have the right where the tiles on the board are in the correct places. So we'll just have a brute force to iterate through all of them and check whether it works or not. Any questions about problem A? Let's move on then. So we have this problem where there is n seats at the stadium. There is A people that will pay with preferred payment method. And then there is B people with the other payment method. So for each place on the stadium in succession, we will conduct a raffle where each preferred person not yet receiving the seat will be given 2 tickets in the raffle, and every other person not yet receiving the seat will get 1 ticket in the raffle. So we raffle each place or until all persons are given a seat, whichever comes first. So we can solve it using dynamic programming. So we need to know probability if there is which means there is already there is I persons with preferred tickets remaining. No, there is I persons that receive the seats that use preferred payment method, and J persons that receive the seat but they use other payment method. So then we can calculate that there is A minus I remaining persons who had not who use preferred method and had not yet received a seat. There is B minus J persons who use other method and not yet received the seat. So total number of tickets is this is the raffle. Depending on and then we need to, so with this probability, we will select a person with that have preferred payment method and go to the in this case, and raise probability of we go here. So after we calculate each probability where this sum is actually n, we can then calculate so if there is some with which probability we will reach this state. And so if we actually use preferred method in this state, we will get the ticket with probability. So we add this to the answer. And in this case, we will of course start with A increased by 1 when we first started our dynamic. Well, and in the other case, we get the ticket with probability this. And so, of course, in this case, we have actually run dynamic 2 times. In this case, we will have B increased by 1. The one corner case was if A plus B is less than N, then we should just output 2 ones. But some of you received not a number, or calculated it the same way and received not a number as a result. So in this case, the answer is this. So any questions about problem B? Let's do problem C. So here we have a graph known as Cactus, which is the graph where no 2 cycles have a common vertex. So in most uses it's almost like a tree. So if you have a problem with a tree that you think is not difficult enough, you can just replace tree with a cactus, and the problem somehow became difficult enough. So let's first solve the same problem on a tree. We can first select center of a tree. Center of a tree is either a vertex or an edge. Then we solve the problem for all subtrees of this tree. So suppose here the answer is then the answer for the whole tree is multiplication, product of all a's times. We also need to calculate the number of ways we can change. So change this subtrees. So they're the same. So we basically need to find how many unique, how many equal subtrees there are, and for that we need to encode them in some way. So after we encode them, if there is like suppose there is that much number of some subtrees, and there is that much number of some other subtrees, and so on. We also add this. So multiply the answer by this. How do we encode our subtrees? So the easiest way to do it is, suppose we have, let's assign number 1 to be of single vertex. Then for some other, we are currently talking about rooted trees, of course. Then if there is some tree that is not yet known, we can encode all these subtrees into some numbers. Then if we sort them in order, so from left to right, from the smallest to the biggest one, because this is numbers, we have some array. And then we can say that, then we can assign next number not used, and it will be equals to this array. So we can then easily go find whether we already have such a subtree or not. So in this case, we can just add a vertex here and proceed the same way. But unfortunately, we don't have a tree, we have a cactus. So what do we do? Actually, for each cycle, we add special vertex that connects to each vertex of this cycle. And then we remove these edges. We need to remember the order of these vertices. So, and we mark this vertex as special cactus vertex. In this case, we can just change vertices in any order. If this vertex is not the root of whole tree, then there is only two orders possible. So one of these vertices is actually its parent. So we can either go from, so we will, for this part, we can, if this subtree equals to this subtree, this subtree equals to this subtree, we can only multiply it by 2. Because we can either get the cycle in this order or in this order in our automorphisms. And if this vertex is actually a parent of the whole tree, root of the whole tree, then we need to find all cyclic. So we can assume this is a string actually on these numbers. So we have a string like this. And we need to find all cyclic shifts that will make the same string, and then also all reversals and cyclic shifts that will make the same string. So for cyclic shift, we need to use any string algorithm that will find us the smallest cyclic shift. For example, that algorithm or Morris-Pratt algorithm. And then just multiply by the number of cyclic shifts. And if reversed, it can be reversed and rotated to B itself, we also need to multiply it by 2. Okay, so any questions? There should be some questions. Alright, we will skip problem D for now because we will need to talk about the algorithm used for this program in more detail. So problem E. As you may probably know, if someone called easy, it doesn't mean it's easy. So we have some polygon, convex polygon. And we need to find the rectangle of the maximum possible area that lies inside this polygon. So let's start. Suppose we want to find a function this function which is for given width and for given x coordinate we want to find square of the polygon, maximum possible, that have width w, and which left side has coordinate x. So how do we do this? Well, it is, suppose we have, for each x, we have, unless there is a side of the original polygon, with this x, we have 2 points, we have 2 points on this x, or 0 points, but whatever, we always have some min-x, min-y. And we can find these values using binary search first to find the side of the original polygon where this line intersects the polygon, and then using line intersection we will find the point itself. So here the answer is so this function is like this, equal to this. We can skip this part because we are actually interested only in the maximum of this function, and obviously that maximum, even if the maximum is less than 0, we just not interested in the splits and so on. So we have this function of x. It can be shown that this function is actually what is this? Like this. So we can use ternary search to find the maximum for any given w. So let's say that f So we can calculate this function for any v's using ternary search. And then apparently this function is good as well. We can also use ternary search on this function. So basically our solution would be to first have outer ternary search on W. And for each W we need to calculate these. We calculating this by using ternary search on this function. And we calculate this function by using binary search to find values of this function. So the problem is somewhat easy indeed. We need just to use ternary search of ternary searches of binary searches. Any questions? Alright, let's move on. Problem F. Problem F. We have 9 string of length 9 consisting of digits and letters. So for example, which is registration number of a car. We also have some mask on the registration number of a car, so it consists of letters, digits, and asterisks. And the numbers match the masks if we can replace asterisks with some digits and or letters, so that we get our number. So we were given mask, we were given some numbers, and we needed to find all the numbers that correspond to this mask. But well, we just go one by one. Check whether it corresponds, and we are done. Okay, we will talk about our regime a little bit later as well. Let's move on to problem H. So here we want to find number of subsegments of this array, subarrays of this array, so that XOR exclusive OR of their values is equal to n of their values. So first we calculate XOR of all prefixes of the array. So say x I so it's and so on. Then for some subarray from I to j, the XOR of this subarray will be this way. Now, for each binary digit, which we have at most 31 of them, 32. Okay, 32. We have 32 binary digits. And for each position in the array, we can find the first position in the array after this one, including this one, which have 0 in this digit. We can find it in n times 32 time by going from the last one. Copying, so here in the last one we notice which digits are 0 and set it to this. And for each other digit, we say that the next time they will be 0 is at infinity. So next, for this one, we just copy values from here and update those of them that have 0 digits in this number, and so on. So now we would go from left to right, and for each position I, we will calculate the number of cases where XOR is the same as AND, starting from this position. So we can actually divide the whole remaining array in no more than 33 pieces, where for each piece, if we have something with j here, they would have the same end on all this from here to here, from here to here, and so on. Same value of end. We will use various calculators in the dynamic to do this. So basically, find the first position where there is 0 in some digit. Until then, all digits are actually ones. Then we find the next one position and so on. So we turn off digits one by one. As there is 32 digits, we can turn off digits 32 times. And so there is no more than 33 pieces. Now for each piece, say from J1 to J2. For each piece, we know the value of end of such subarray. So we need to find we need to find the value of positions where it has the same value of XOR. So we can, in advance, we can have map of like for value of xi that goes to the positions where it achieves that value. So now we need to we know the value that we need to achieve some value of x. We look at the positions where this value is achieved, and using binary search, we find all values between J1 and J2. So then we sum this over all for each piece, sum this for each starting position. So the total complexity will be n times log maximum value of A times log n. So any questions about this one? The values in the map is basically sorted list of all indices where the x is equal to given value. So that is from value to the list of indices where this value is achieved. Next to the problem I. Problem I is an interactive problem. It's the kind of problem I think that mostly that is like exclusive to the Narcissistic European regional competition. So here we have a random control system. We have like a rocket that goes from some point, from some starting point, and has some starting speed that is from this. So each second we can query some segment of the given some segment of the line. And then the answer for the query is whether the the rocket is currently inside this segment or not. And then, after this, the rocket travels for 1 second, so it adds its speed to its coordinate. And then we need to sometimes, at some moment, we need to answer where the rocket is. So, how do we solve this? For each position, for each speed, there is at most this number of possible speeds. We store an array where this where can be the starting position of the rocket at this speed from some minimal value to some maximum value. At the beginning, minimal value is 0, and maximum value is p. So we have this values for all speeds, for all possible speeds. Now, on each step, we use binary search. So that original, we want to make only queries on the form check 0 something, and we want to find such x so that we roughly divide in half the number of possible starting positions. So for each known x, we can then find how it will divide the each minimal to maximal segment. So we calculate this overall speeds, and we can use binary search to find such x so that the starting positions will be divided roughly in half. That way, each time we have the possible amount of possible starting positions, there is total of this number of possible starting positions. So in logarithm modes, we will find what the actual starting position was. So, any questions about this? Okay. So problem J, we were given some message in Twitter social network, and we needed to find the long modest conversation. So each message can be actually interpreted as some identifier of the author, and then some mentions of other authors. So we need to exclude author from these mentions, and then we go from top to bottom. For each author, we need to store we need to store the longest conversation so far that ends with the message of this author in some map. And for each message, we need to remember then for each message we can find the outer with and also not only the length but also the position, the idea of message that that achieves this maximum. So then we go through this through the mentions of the current message. We find the one with the longest conversation, and we say that okay, this is the last. We update the map for outer, and we also say that for this message, the previous one was at this position for the chosen mention. So we go on. In the end, we find, after we process all messages, we'll find the maximum value of length in the map, and going by last values from there, we reconstruct the whole conversation. Any questions about this one? Problem K. We have a game which is simplified version of the game Kabaleo. We had our color, that is color, and each player, including us, have chip of one of the colors. And there is also some chips already on board. So each turn we can put each player picks their chip and places it on top of some chip already placed in the board. And our target is to have the most chips of our color, no matter how other players are playing. So other players will always try to close chips of our color. If there is the amount of chips of our color after our move is less than no more than amount of remaining players, then we automatically lose. And so there is no winning moves. And so we can assume that after we play our chip, after that these chips will replace chips of our color that are currently visible. So we need to calculate actual distribution of colors at the end. Before we go, we take our move actually. Let's note that we only need to look at the two maximal values of other chips, because we can cover the chip of only one color, and if it is the current maximum, we only need to look at the second maximum. And so then we check every position and see whether we will win if we put chip in this position. So, any questions about this one? Then let's have a 10-minute break, and then we will discuss the two remaining programs. We have some kind of landscape. We have a sound that goes in some angle, and then we have some what's called solar panels, which can be mounted at some point, but the heads of them are here. So the first thing to do is rotate the whole picture so that the angle of the sun becomes from being the x-axis. Then there is some minimal value by y and some maximal value. So we should mount the highest panel at the maximal value, and then we should mount other panels in such a way that first they are mounted at the first possible point where the given height intersect our landscape. And also, so the new solar plane would not cover any points of the previous one. That way, the total covered length covered by sun will be, so suppose it's so as all the solar planes will be fully covered by sun in this case, or we will have this amount of panels covered by sun, which is the maximum achievable. So if we reach this point and like there is still some panels remaining, you can place them in any place, because they won't help and they won't harm as well. So you first rotate the landscape by an angle of the sun, and then calculate the first intersections for the levels that we need, and then rotate them back to have the answer. So, any questions about this one?
How do you got this problem? How?
Well, you basically rotate this, right? Then for each segment, you going from left to right, you see what part of it is visible. It's some part from this. Then when you need to have some line here, you see what segment is visible here intersected. And then for when you get the points in these coordinates, you just rotate them back by angle minus alpha. I didn't know the answer. Anyone else? So, okay. So the remaining problem is problem D, which presents us an interesting theory. So we can have so here we need to construct some kind of structure that is almost a tree, but not quite. In tree, we need to be able to read each word starting at the root, right? Here we can start at any point, but we need to go down the tree, and we need to read this set of words given in the program given to you in the input. So let's build a graph with n+1 vertices. So the vertices is our words, and vertices is our words. And there is additional vertex that corresponds to empty string. Then we will build edges from each vertex to each other, where the weight of the edge would be, so let's say we have an edge from S to T. So weight is, if T is something of S, then weight is 0. And otherwise, it's the number, it's the length of T minus biggest, longest suffix of T, longest prefix of T, that is suffix of S. So it's basically how many letters do we need to add to the end of S so we can read T somewhere. So we build this tree. It can be shown that the answer to the question is actually the minimal weight of the aberrations in this tree. If we start with the root in the vertex that corresponds to the empty word. Okay, we can also construct some easier tree. So for each word, we will take any all prefixes of this word. So we have some vertices. Say we have words ABA and AC. Then we have vertices for this works. Because both prefixes of AC, empty and A is already in here, the AC itself. So here we will have the vertex from the sum word W to word WL, where L is the letter with the weight 1. Yes? And for each word W, we would have edge of weight 0 that goes to the suffix of W if it present here. So here there will be word from ABA to A with cost 0. And here it is easier to show that if we find the minimal absorbance of this tree, of this graph, with starting here, we can just then condense 0 links, and we'll have a tree that requires the problem statement. But how one finds minimal, such almost minimal spanning tree, but with directed edges and with root? So there is a special algorithm for this. It was devised independently by group of Chu and Liu and by Edmonds in the 60s years of last century. So the algorithm is like this. So we need, basically we know that for each vertex but the root, there is some edge that going into this vertex and there is only one such edge. Right? Then we can try to use exactly these edges. So for each vertex there is some exactly single incoming edge that is the edge with the minimal weight. But if there is no cycles, so it is a tree, then we are done. Everything is okay. This is obviously the minimal total weight, and we are done. But what if there is a cycle? So we choose any one cycle, doesn't matter which one. And then, so we have a graph of G. So we have vertices, edges, and weights of the edges. So let's create a new graph. Where so let's call the cycle C, is so all vertices that are not on cycle, and also the special vertex that will represent the cycle itself. Then, for edges, if edge have both, so let's say the edge goes from V to U. If both of the vertices is not don't lie inside the cycle, Then we just add this edge to the new graph. If the source of the edge is in the cycle and the destination is not, then we add edge from the new vertex to the original destination with the same weight. And if vertex is not on the cycle, source is not on the cycle, and destination is on the cycle, we add edge from the source to the new vertex, but its weight will be the original weight minus, so suppose, let's say that if this vertex P, the previous one is P, so weight will be weight of the edge minus weight of the edge in the cycles that go into the same vertex. So now we can find, and if the edge lies inside the cycle, we just delete it. So now we can find minimal sense of this new graph. It contains smaller amount of vertices, so the process is finite. And then we just, we have some, exactly one vertex in the substance that go into C. We find such corresponding edge. And so we add all edges, this edge, and all the edges that was in the cycle, but the edge that going to the same vertex. Each step of these algorithms work in this time. And there is no more than these steps. So the total complexity of this algorithm is this. There is ways to optimize this algorithm that would read in this time complexity, but there are other parts. It's unlikely that you would need to use these optimizations in the contest. So you can work with this one. So any questions about the algorithm itself? So I will send out the link for today's contest in a little bit time. It will be on the same system, so you will use the same logins and passwords that you used last day. And so now you can come to me and ask any questions that you are not comfortable to ask in public. I will gladly answer them. Otherwise, the contest will start about, as usual, 15 minutes before 1 hour.